Uh, Welcome, Deniz Mودer, Head of Application Engineering in Incos, the stereolithography first company in metal 3D printing. The innovative technology, she will introduce this technology to the medical and dental field. Thank you very much. The platform is yours.
Thank you very much. Yes, so we got asked to make a little presentation about patient-specific metal brackets using lithography-based metal manufacturing. Because nowadays other technologies like powder bed fusion, selective laser sintering are used, but we don't reach the proper requirements for the quality of the parts. So this is where our technology comes forward. So I've been working at Incus for over four years, and I was really impressed by the technology already at the beginning before starting here, and seeing how fast we move forward and what we can achieve is really impressive. So yes, so Incus was founded end of 2019 as a spin-off of the ceramic lithography-based manufacturing, the company called Lithos. So we are the system provider for lithography-based metal manufacturing technology, and we really want to provide to the customers the whole technology and the whole know-how to make sure that our customer is able to produce the parts that they want to produce. We have already over 20 machines sold worldwide, and we really focus on getting the best experts worldwide with a team of 28 people. We have over 14 different nationalities. And finally, we have one of the big investors of additive manufacturing technologies believing in us, IM Ventures. Lithography-based metal manufacturing has it already in the name. We have a vat-based method, so a light-based method, polymerizing actually a slurry that contains the metal powder. So everything is homogeneously mixed inside this slurry. The slurry that is more body-like, so it's solid at room temperature, and it's liquefied by a blade. We will see a video in the next slide. So after the printing process, we have still to undergo a debinding and sintering to remove all the binder content of the parts, and the sintering to really densify the metal particles that we mixed in. Thanks to a highly a good quality coating system, we really reach superior surface aesthetics. Thanks to having the lithography, we have the really good exact parts and the nice yes really good precise parts that we want. And finally, having it combined in a slurry that is photoreactive, we don't have any loose powders that we need to work with, and changing materials if needed only takes 5 minutes. So to have a better idea how it works, there's this little video. There's the heated blade that is taking the material that is liquid onto the build area where the light is being projected by layer. And this continued again and again until we have here the material solidifies again. So you don't need any support structures, and you can actually work your way in the Z direction and add parts on top of each other. What we can see now is what comes out of the printer. This goes then into the decaking, what we call decaking station, where basically with hot air, we will remove all the material that has not reacted with the light. and have coming out of it the parts that we printed. All the material that comes out of it can be reused, recycled for the next prints. So we try to really make the most of all of the material that we use. This first machine here is a Hammer Lab 35. It's our plug and produce solution. It's really easy to install, really easy to use. It has a build volume or build area of 56 times 90 millimeters and can go up to 120 millimeters in height. It has a pixel size of 35 micron that will contour and design the parts. And we can have different layer thicknesses from 10 to 100 micron, while we normally use for stainless steels more around 25 or 30 micron to really have the resolution and the surface quality for the small parts. Here's an example of the economics for dental brackets for the Hammer Lab 35. So with this technology, and since the brackets are rather small, we have an annual capacity of over 850,000 parts yearly, which comes down to a print cost of 8 cents per part. But to go even to the next step and to the higher production, we also developed our Hammer Pro 40, which is really thought for high production, bigger parts. It has a little robotic arms, being able to take any material that is missing for the feed, or it can also take any already printed block out of the machine that you can grab then anytime. So this will really just start the next job, take the finished job, and go on. So barely any need to open the doors with this printer. This printer has now a build volume of, or build area of 2 times, so there are 2 platforms of 200 times 77 millimeters, and can go up to 150 millimeters in height. There is a small mistake in the slide. Yes. Otherwise, the print speed is the same with this printer, while the production will be much higher. You can see it here. There are the 2 build area, the build platforms. And with this machine, we actually get to an annual capacity of over 7 million parts yearly, which comes down to a 2 cent per part cost. So this is really when the production productivity needs to be much higher. Just to give an example of the comparison with the powder bed technologies, not including binder jetting here, but for everything that is related to powder bed fusion, selective laser melting, or selective metal sintering, we only can get feature sizes of 100 to 140 micron. We need support structures for those parts, and we had a really rough surface here. In comparison, we have really a great surface aesthetic at the end. We are similar to what people know usually in the metal injection molding industry, with a surface of roughly 2 micron RA. We have a high repeatability. For example, we measured the slot width of the brackets. We are less than plus minus 20 micron. I mentioned already we don't have the support structures, and the polishing or manual rework of the brackets is really minimalized. And additionally, it's an easy technology to operate with. The mechanical properties of our stainless steel 316L or also our 17 4pH are the same than we get for metal injection molding. We also have our experience with titanium, where we reach also the mechanical properties needed for technical applications. And our aim is at the end of the year to really have the medical grade chemical composition of our titanium as well. Here's just a small video to show as well the how the journey of a bracket could look like. So we put the material into the printer. So you see my colleague here putting the raw material in, looking if the job looks great on the printer, and started the print job. Then we go to the decaking station. We melt everything off that has not reacted with the light. We put it in an ultrasonic bath. And after this, the parts are clean and can go to the post-processing, which is the debinding and sintering. Since the metallic brackets are really small, the time for sintering is also not long and can be reduced. While we have the experience with parts going from small brackets to much bigger parts, we do believe reducing the time for the brackets is definitely possible. Here's an image of a synchrotron, a 3D scan or CT scan of one of our demo part brackets, and you can really see inside that the porosities are close to nothing. I think this is one of the last slides, just showing polished brackets and as sintered brackets. So this one will have a surface roughness of roughly 2 micron, while this one here has it around 0.50 micron. So achievement with our technology, no supports needed, surface roughness of 2 micron in every printing direction without any surface treatment. There's an automation process possible for the decaking, thanks to the high green strength, as well as for the cleaning of the parts. And the surface treatment after sintering is the same than any traditional manufacturing. And finally, a small summary so that everyone can have a good view of what is possible with that technology. We can do complex parts in MIM range. Actually, we can go in sub-grams. 1 to 200 is more the MIM size range, but we have parts that are in milligrams. No support structures needed for printing, which reduces any manual labor that is known after 3D printing. Good green part strength, one of the highest resolutions and surface aesthetic for metal additive manufacturing. And while now I mentioned only the stainless steel and the titanium briefly, we do have the possibility to print any types of metals, whether they are flowable or non-weldable, with that technology, as long as sintering is a possibility. It is a very simple production process and a really safe working environment, since we don't have any metal dust around and no high-powered laser. And this was it for me. Thank you very much.
Thank you very much, Denise. It's very interesting information. There is some question. It is amazing that there is no support, especially in the fine parts,
Exactly.
like hex of implants and these parts. If we put support, it's very difficult to clean. So it is amazing technology, and it is the quality is compared with laser is more accuracy in the detailed surface.
Yes.
One question is about what available metals that we can print in this. I find on your website titanium 64 and stainless steel 316. What other material also possible? Any material possible to paint or any powder metal?
Yes, really a lot of materials that we've printed already. We have a lot of experience now with copper as well. We had diamond composites, we have tungsten alloys. We even printed precious metals. We printed red gold, white gold, yellow gold. So a lot is possible. A lot is possible. Also cobalt chrome that you mentioned earlier in an email. We've printed cobalt chrome. We have some sintered parts, but we didn't have a big focus on it yet because the demand was not that high. But it is possible, and yeah. So really, if there's any request of material, I'm pretty sure we've seen it before.
Yes. And it is, for example, the technology is compared with MIM metal
Yes.
injection method. It is same powder particles, or the post-processing
Yes.
is similar. What is the difference between
exactly? So with metal injection molding, the only issue is that you need a mold for one part. So these molds cost a lot. So if you are not making the same bracket over and over, this will not be the right choice of technology. Using additive manufacturing, you really have the freedom to do custom made parts. You can easily change the geometries and start a print. The print job will just take 30 minutes to 2 hours, depending on the size of the parts. So you can really have a really high throughput iteration.
And
otherwise, in terms of debinding and sintering, it's very similar.
Perfect. And the gas is nitrogen, or what you recommend, argon or nitrogen for post-processing?
It depends on the metal that you will be using. For 316L and 17.4 pH, it's usually recommended to use hydrogen, but it is also possible, because a lot of industries don't really want to use hydrogen in their buildings. It is possible to use forming gas as well.
I find also you use two kind of binders on your website. Is there any difference, or what is the difference between the two types of binders?
In the case of the ones that we have on the website, it is really a matter of really fine structures. But when I say really fine structures, it's even smaller than the dental brackets. Then we have a specific binder that we prefer to use. However, our main binder works for most of the materials and will be the best choice if it goes to the bracket industry. So during the printing, there will not be any issue of distortions, but during sintering, the parts, since the particles need to get together and shrink a little bit, we have an estimated 20% shrinkage that we can either already include in the design of the geometry of the parts, or in our software we have an easy way to just set the shrinkage values or the compensation values.
You try also to print implants with threading and some screws or something with titanium powder?
Yes, we actually have some examples of titanium implants. I mean, example demo parts that have really small threads. threads are really not an issue. That's where we really can use the lithography, the light-based system, to have really perfect accuracy with any threads or screws.
If compared with SLM, not possible to make the 3D for implants because of the roughness of the laser melting.
Yes. Yes, as I showed in the one slice with the selective laser melting, they even mention on the website that the minimum feature size is 100 micron, and we work with a projector that has a pixel size of 35 micron, so we can really get small details.
So the powder of the laser, selective laser, is 30 microns, most between 45 to 30 microns. The same powder is possible to use with your binder, or we need?
It is possible. Yeah, sorry. It is possible to use coarser powder as well in our technology, but we do prefer to use the ones similar to metal injection molding, which is 5 to 22 micron, considering the D10 and the D90 of the powder distribution. And it is also possible to go to even finer powders if the details and the surface needs to be even higher than the under 2 micron that we can achieve.
Okay, so I suppose we answer most of the questions. Thank you very much for your presentation. And this presentation will be published on the YouTube channel of Arab Dental Labor Magazine. And we'll send the link for all the dental technician and dentists who didn't attend. Okay. Thank you very much.
No worries. Thank you.